Hey everybody, Trey here. Welcome back to another video. In our previous video, we took a deep dive into the Matador, Texas EF3 tornado from back on June 21st, 2023. Well, on that same day, there was actually a separate northern mode that was quite a prolific tornado producer in and of itself, and that was thanks mostly to a single supercell in northeast Colorado that produced 27 different tornadoes all on its own. Just an incredible number of tornadoes to be spawned by a single supercell. So in this video, we're going to take a deep dive into that tornadic supercell up in northeast Colorado. We're going to take a look at the background pattern, some of the meteorology behind the event in this northern portion of the risk area. And we're also going to take a look at some of the storm behaviors that this supercell displayed to try to decipher why this supercell was able to produce 27 different tornadoes. Most of them were short-lived, but there were a few beefy ones in the bunch. But still, 27 is just an incredible number. You see some amazing footage here from Tony Laubach of one of the main tornadoes with a satellite rotating around it. Just some incredible footage there, and this was certainly a prolific tornado producer up in northeast Colorado. So, without further ado, let's go ahead and get started. As always, I'm going to put a link to the official event page from NWS Boulder in the description box below so you can do some research on your own. It has all of the tornado tracks listed, each of the 36 total tornadoes on this day, along with pictures and the ratings there. And it also has some very nice photos of the damage and some radar animations as well. So as we talked about in the Matador video, the day started out with a very broad slight risk from the central high plains down into central Texas. And the main tornado risk was situated there in far southeast Wyoming to very far northern Colorado, really not encompassing the Akron area, which eventually would see that cyclic tornadic supercell. There was also a threat for damaging wind and large hail, and by the 1630 outlook, so the midday outlook, they had increased the risk to an enhanced risk in both the southern mode and this northern mode, and they had also nudged that 5% area down to the south a little bit, farther into northeast Colorado, with a threat for damaging wind once again and significant severe hail that had been bumped up since the morning to a 30% hatched area there for that southeast Wyoming, western Nebraska, and eastern Colorado corridor. But when we'll talk about here in just a bit why the tornado threat was nudged to the south a little bit and the eventual focus for tornadic activity shifted from southeast Wyoming into northeast Colorado by early afternoon. All right, let's dive into the meteorology behind this prolific tornado producer. We'll start out at 500 millibars, as we always do, and we'll start out at 12Z, 6 a.m. Mountain Daylight Time on June 21st. We talked in the Matador video about how the pattern, at least in the upper levels, was fairly quiescent for significant tornadic activity, especially across the southern mode. We noted just only a little bit of enhanced flow here rounding the top of this ridge centered across northern Mexico. Up here to the north, in the northern regime, we were a little bit closer to this highly amplified trough here across the northwest, across eastern Washington, Idaho, down into Nevada, with some strong flow here in the exit region of this trough up into western Wyoming and Montana. But here in the middle, southeast Wyoming into Colorado, we were kind of stuck in the middle between this ridge to the south and this trough to the north. Just a barely glancing blow here across southeast Wyoming, and not much to speak of as far as synoptic scale forcing for ascent across northeast Colorado. Only about 20 to 30 knots of flow here at 500 millibars across this region, and that would stay put through most of the day. Couple of shortwaves rotating through the main flow here. You see a little bit of a kink in the flow here across Wyoming, but that might be just a little bit farther north from our main area of interest to really have any sort of impact on the environment. So really not much in the way of synoptic scale forcing for ascent, especially with southern extent here across northern and northeast Colorado. The main forcing mechanism in this case was significant upslope flow. We've talked about upslope flow on the channel before. It's basically when you have low-level flow that interacts with a substantial terrain feature, such as a mountain range. Well, that low-level flow can't go through the mountain, so what happens is it's forced upward, and under the right ingredients, this forced ascent can provide thunderstorm activity, especially on the windward side of that mountain range. Now, again, we're talking about the low-level flow, particularly the surface flow. So let's go ahead and go down to the surface and see what we can decipher. We'll start out with our broad surface map here, and you can see that we don't really have any notable or intense surface lows across the western half of the country. Really just broadly convergent weekly cyclonic flow from the central high plains down into Texas. You can see the winds here across New Mexico, Colorado, into Wyoming, out of the west, and across Texas, western Oklahoma, western Kansas, and Nebraska, winds more out of the east. So just weekly convergent, weekly cyclonic flow here out across this region, and that would not change much throughout the day. You see here as we go through the animation here, we really don't have any significant areas of lee cyclogenesis on the east side of the Rockies. And that is to be expected. We talked about how this upper level trough here at 500 millibars took a more northeasterly path into Canada rather than making a little bit more eastward advance into the central high plains, which would in turn allow that strong flow to traverse the Rockies a bit better, a bit more efficiently, and create a little bit more lee cyclogenesis here just to the east of the Rockies in Colorado or Wyoming. But not really the case given the path of this trough and its enhanced flow aloft. Now, the lone exception may be down here in far southern or southeast Wyoming, a little bit of a closed contour there, indicating possibly some weak lee cyclogenesis at the surface. We did talk about how with northern extent here into Wyoming, we had a little bit more of an influence from this upper level trough. Even though it was a glancing blow, we still had a little bit more interaction with the trough up here as you went up into eastern Wyoming. So that could have initiated some very weak lee cyclogenesis, although there are some terrain impacts to talk about as well. We'll talk about those in just a second. But now let's go down to our raw surface data to get a little bit better of a picture of what was going on at the surface. The first thing we can make out is a frontal zone draped across western Nebraska into eastern Colorado. Once again, this is at 12Z, 6 a.m. Mountain Daylight Time on June 21st. This front was associated with a surface low all the way up in southern Canada that we can pick out on our broad view surface map here. See this little closed contour here? That is our surface low, cold front draped well down to the south into the central high plains. And we can really easily pick out the location of this front using our raw surface data. First of all, there is a pretty clear wind shift across western Nebraska into eastern Colorado. We see winds across Wyoming, far western Nebraska into central and northeast Colorado are generally out of the north, while that shifts to more of easterly or east-southeasterly flow across central Nebraska, northwest Kansas, into far eastern Colorado. So a pretty clear wind shift here across this region. We also have a pretty clear temperature gradient as well. Temperatures in the low to upper 60s here across far southeast Wyoming, western Nebraska, northern Colorado, even colder temperatures back to the west, with 70s temperatures across southwest Nebraska into far eastern Colorado and northwest Kansas. So our frontal zone generally is going to be somewhere in this vicinity right here. Pretty clear wind shift and pretty clear temperature gradient across that boundary. This front would make very little eastward progress throughout the day, and eventually we would really wash out that wind shift along the boundary as we would establish post-frontal upslope flow on the western side of the boundary. We'll talk more in depth about the upslope flow here in just a second. But this boundary was definitely not a main factor in the significant tornadic activity across northeast Colorado, as even though there were some storms that fired along this boundary in western Nebraska and far northeast Colorado earlier on in the day that produced some severe weather reports, including a couple landspout tornadoes, the Akron supercell was definitely in the post-frontal regime behind the boundary. Now you'll see once again that the winds begin the day very much northerly behind the front, and then as we go into the afternoon, they start to begin to shift to much more easterly winds across northeast Colorado and southeast Wyoming. That is that upslope flow becoming established, and this is a fairly common practice in the central high plains. Oftentimes in these central high plains severe weather setups, you'll have a front move through either the day before or the morning of an event, and the winds behind the front will begin as northerly or northwesterly in the morning, and then during the afternoon they will shift to easterly, flowing up slope. This is based on the physics and dynamics of sloped surfaces, and I won't go too deep into the weeds with the science here, but we can consider eastern Colorado and Wyoming as a sloped surface. Here's a topographical map of Colorado as an example here. The green colors are your lowest elevations, and the purples and whites are your highest elevations. So of course we have our lowest elevations out here to the east across eastern Colorado, with our elevation gradually increasing until we get to the highest peaks of the Rockies out here to the west, just west of Denver, for example. That is a sloped surface. As you get surface heating during the day, you'll see a thermal gradient start to develop with warmer temperatures out here on the lower terrain and cooler temperatures out here on the higher terrain out west. And in turn, a pressure gradient develops that goes from the warmer temperatures, higher pressure out to the east, toward lower pressure, cooler temperatures out to the west. And because the wind is modulated by the pressure gradient, your winds begin to flow up the slope, i.e. upslope flow. So this happens on a very regular basis in this part of the U.S., and of course, it can be accelerated if you have lee cyclogenesis. In this case, as we've discussed, we really didn't have that process taking place due to the orientation and the motion of the upper level trough, except for perhaps in southern Wyoming. You see, as we get into the mid-afternoon hours, this is 20Z, 2 p.m. Mountain Daylight Time on June 21st, that we have a very modest cyclonic circulation beginning to develop out here across southern and southeast Wyoming. This could be a manifestation of some small degree of lee cyclogenesis in this area, helping to really back those winds across southeast Wyoming especially. Now, there's another topographical piece to this as well, and we've talked about this before for Colorado, but not so much for Wyoming. As we talked about before, there's a phenomenon called the Denver Convergence Vorticity Zone, or DCVZ, that often develops in the spring and summer when easterly or southeasterly flow goes up and over this elevated terrain feature called the Palmer Divide or Palmer Ridge. This area of yellow and red there you see on the map, this topographical map of Colorado, just to the southeast of Denver. That is the Palmer Divide. It's a little elevated terrain feature. And when the easterly flow goes up and over the Palmer Divide and interacts with flow coming off the higher terrain of the Rocky Mountains, we get a convergence zone to develop in the vicinity of the Denver metro area called the Denver Convergence Vorticity Zone, or DCVZ. So this convergence boundary can foster thunderstorm development and can aid in both landspout and supercell tornadogenesis, given enhanced surface vorticity or spin along this boundary. And the associated phenomenon known as the Denver cyclone can also develop as well if a large gyre or circulation develops in this regime. Well, there's a very similar phenomenon that occurs in southeast Wyoming called the Chugwater cyclone. In southeast Wyoming, you have a very similar feature as the Palmer Divide called the Cheyenne Ridge. You see this area here near the town of Cheyenne there in far southeast Wyoming, this area of yellows and reds. That is the Cheyenne Ridge. And once again, as low-level flow out of the east or southeast goes up and over this ridge, and it can interact with flow that is modulated by the Laramie Range right here. These purple peaks right there, that is called the Laramie Range. And flow in the vicinity of the Laramie Range is modulated by those mountains, and you can get a circulation to develop just on the east side of the Laramie Range, just north of that Cheyenne Ridge. You can get an area of cyclonic spin and vorticity there, and that can enhance the tornado potential with any supercells that can interact with this circulation. I'm a little skeptical we had a full-fledged DCVZ develop on June 21st. Keep your eye on the Lyman wind barb, which is right here. Lyman sits right on top of the Palmer Divide. And you do eventually see it flip around to easterly by about 19Z, 1 p.m. Mountain Daylight Time there. But you don't really see any super clear convergence in the surface winds as you go into the afternoon, which is the case for a typical DCVZ event. You'd often see the winds coming right at each other out of the northwest here on the north side of the metro and out of the southeast over the Palmer Divide up into the Denver area, really clearly defining that boundary. You don't really see that here. Somewhat chaotic flow at the surface, at least depicted by our surface data here. But it doesn't really matter in any case because the DCVZ, of course, forms near the Denver metro area, and Akron is all the way out here. So it would not, that Akron tornadic supercell would not have been impacted by the DCVZ anyway. But certainly to the north, the Chugwater cyclone was alive and well. It's a little tough to see on this map because we have an overall lack of observing stations here in this part of the country. But we did talk about that broad cyclonic flow you see on the surface obs here in southeast Wyoming. That could be in part due to some weak lee cyclogenesis, and also could be some impacts from that Chugwater cyclone. Again, if we had some more observing stations in this region here, we would probably be able to see it much better. But the Chugwater cyclone certainly was alive and well as that flow finally turned to easterly here. It went up and over the Cheyenne Ridge and definitely started to create some of that circulation, which would sit in place just east of the interstate here, north of Cheyenne, up toward Chugwater and Wheatland, waiting for any supercells that would fire on the higher terrain out to the west to utilize that enhanced spin and possibly produce tornadoes. One more note on the surface data before we move on. We started off the day with impressive moisture for any region, but especially for the central high plains. Here we are at 12Z, 6 a.m. Mountain Daylight Time, and we have mid to upper 60s dew points entrenched across much of northeast Colorado into western Nebraska, with even some 70s readings from extreme northeast Colorado into southwest Nebraska, 60s dew points up into eastern Wyoming as well. And this continued into the afternoon. As we play the animation here, you'll see those 60s and 70s dew points stay put by 20Z just before storm time. 82 over 70 here at this station in northeast Colorado, with mid to upper 60s dew points across the entirety of northeast Colorado. upper 50s to mid 60s there in southeast Wyoming as well. Anytime you see this high of moisture when forecasting for these areas, that should set off immediate alarm bells that something interesting might happen. As we've discussed before, a parcel of air at higher elevations is unable to hold as much moisture as that same parcel of air at lower elevations. So a dew point of, say, 60 degrees Fahrenheit at Cheyenne, Wyoming, or Denver, Colorado is like a 70-degree dew point in the lower elevations of, say, Oklahoma or Texas. That's why you don't need super high dew points to get notable tornado activity in Colorado, Wyoming, etc. I've seen plenty of Colorado tornado events happen with dew points in the 40s, even the 30s on rare occasion. So when you see dew points in the 60s and even 70s here, especially 70 plus in Wyoming or Colorado, you should immediately take note, as that's like a 75 or even 80-degree dew point in, say, central Oklahoma, northern Texas. And that can often set the stage for some really interesting stuff. More on this as it pertains to the Akron tornadic supercell in just a bit. So that pretty much does it for the important synoptic and mesoscale features pertaining to this event. These big Colorado tornado events never really involve a strong surface low, a strong low-level jet that you would often see with big tornado events, say, in the southern plains. They're all predicated on the distribution of surface vorticity, topography, etc. And just to show you the 850 millibar pattern from June 21st, here it is. And as we talked about in the Matador video, really just broad, weak cyclonic flow for much of the day across the western half of the country. You see here, just broad, weak cyclonic flow here, no more than 10 to 15 knots across southeast Wyoming, northeast Colorado at 850 millibars. So not the large looping photographs you might see in the southern plains or the southeast. We're really relying mostly on that surface vorticity amid a favorable thermodynamic environment to get the job done. So I was out chasing on this day with the tours, and we decided to target up in southeast Wyoming. The main reason was that low level and deep layer shear was expected to be a bit stronger up there versus northeast Colorado. I did see those 70s dew points up in northeast Colorado just sitting there that morning, and it did give me some pause, but I just could not get past the paltry photographs in that area that were expected to persist into the afternoon. It appeared that deep layer shear would remain weak for much of the day in northeast Colorado due to being a little bit farther removed from that enhanced flow aloft associated with that northwest upper trough. Therefore, it looked like more of a mix of multicells and maybe a couple supercells embedded in there, but mostly a mixed mode that would not be super favorable for sustained supercells with significant tornadic activity. Farther north, though, across southeast Wyoming, you had a little bit better deep layer shear, a little bit closer proximity to that stronger flow aloft, and some additional influence from that weak lee cyclogenesis, as well as that chugwater cyclone in place, with still very impressive moisture for the region, upper 50s to mid 60s dew points here, still very, very high for this part of the country. So it looked like that was the place to be, and SPC seemed to agree with that based on their placement of the 5% tornado risk area that morning. So we headed toward the Chugwater area or just west of there and waited as storms began firing on the higher terrain out to the west and southwest, kind of just north of the Laramie area, and we waited downstream from those as they made their way to the northeast. But it became apparent pretty darn quickly that we were in trouble, and that was because of a low cloud deck that would just not go away. Here's a great shot of what was going on. There's a supercell back in there. A storm had fired northwest of Laramie and was moving northeast toward our location, but you can't see anything because of this stubborn low cloud deck here. So along with thwarting visibility, which is usually extremely good out here, you can usually see dozens and dozens of miles out in the distance, it was also thwarting destabilization. I remember it was very cool at the surface. The sun did actually try to peek out for a few minutes where we were as the storm was approaching, but the clouds swept right back in and remained there as we began to interact with the storm. So I knew pretty much right away that we probably weren't going to destabilize enough for a robust tornado threat, but it was too late to adjust back to Colorado. We might still get a tornado or two out of it, but this cloud deck was just not going away, and that was going to be problematic for destabilization and fully surface-based supercells, unlike farther south in northeast Colorado. Unfortunately, I was unable to retrieve satellite data for June 21st. For some reason, the archive does not exist for this day, so I was not able to get full satellite loops for June 21st, but we do have this mesoscale discussion issued by the SPC just after 4 p.m. Mountain Daylight Time, showing at least a snapshot of what the satellite looked like. Here's our ongoing supercell in Wyoming. You can see the bubbly clouds there. The radar is overlain here as well on this image. There's our ongoing supercell northwest of Laramie, moving off to the northeast toward Wheatland and Chugwater. But you can see this batch of clouds there. That is that low cloud deck that was sticking around out ahead of this storm, helping to keep temperatures cool and probably allowing the storm to remain a little bit elevated as it moved off toward the northeast. You can also see some of these stable rolls that we've talked about before, these bands of cumulus clouds that just look like cloud streets. A little tough to see here, but you can see just where under that box that says differential heating zone, you can see some of these stable rolls there, these little cloud street type features. That signifies low-level stability, which of course is unfavorable for fully surface-based tornadic supercells. Down to the south, however, we had fully destabilized. You can see the clouds out ahead of the ongoing storms in northeast Colorado, looking much more bubbly. Lots more bubbly cumulus out here ahead of these ongoing storms. The temperatures had soared into the 80s as well. We'd had full destabilization for much of the morning into the afternoon. So a much more favorable look for surface-based supercells down here to the south as opposed to farther north where we had this low batch of clouds that was sticking around and would just not go away. Plus this batch of stable rolls here signifying not a fully destabilized low-level environment. All right, let's get into some radar data. Here's some data from the Cheyenne radar showing how things initiated. Storms began to fire along that frontal zone out to the east by about 18Z, which is noon Mountain Daylight Time. And interestingly, you'll note that they're moving to the west as we go into the early afternoon hours, which is quite unusual. Oftentimes you see storms moving to the northeast or east, but as we recall, winds aloft were very weak, so not much steering flow to drive these storms. And this really could be more of a result of propagation behind their own outflow. You can see a little bit of a fine line perhaps developing out ahead of these storms, one up here as well, but you also see this secondary fine line out ahead. SBC characterized this as a remnant outflow boundary, but I'm not 100% sure where it came from. There were some storms overnight in western Nebraska and northwest Kansas, but they were not incredibly long-lived or widespread, so I think perhaps they were referring to the outflow that these storms produced themselves on the 21st, although there does appear to be this fine line out ahead. And if we take a closer look here, you'll see from the Denver radar, you can see this fine line here as well, which looks to be some sort of outflow boundary perhaps. It's tough to say because we didn't have a full-on MCS move through the region the night before, which would clearly put out a boundary and definitely be a player in the tornado threat for June 21st. So I'm not 100% sure what's going on here. Certainly if this was a remnant outflow boundary, that would increase the low-level shear and surface vorticity along it. But back to our wide view from Cheyenne, and we'll go back to the start here. You see that storms in Wyoming initiate on the higher terrain by about 19 to 19:30 Z, so 1 to 1:30 p.m. And you can see some of those storm concerns, or some of those concerns we had with the storm mode and that lack of deep layer and low-level shear. You'll see as we go toward the end of the loop by about 21 Z or so, 3 p.m. Mountain Daylight Time, the Wyoming storms were very much discrete and very much supercells. You see two discrete supercells there. You can even see the appendage on the radar here with the southern one and that flying eagle type shape with that northern one. So clearly discrete supercells, sustained discrete supercells in this northern mode. But to the south, you had a lot of storms that fired, obviously influenced by their own outflow. So lots of updrafts there competing with one another. And we did have some severe weather reports early with this activity, including a landspout tornado. Not surprising, as they were along that frontal zone, perhaps that remnant outflow. But these storms were clearly a mix of multicells and supercells initially. You don't really see that classic supercell shape. Maybe a couple in here, but quite a few multicells mixed in as well. So some of those concerns over the storm characteristics being more mixed down to the south due to a little bit more of a lack of deep layer shear were somewhat coming to fruition early on. Let's take a closer look at the Akron area leading up to our tornadic supercell. And for reference, Akron is right in there. And this starts just after 21Z, 3 p.m. Mountain Daylight Time. And this gives us a great look at the fact that the storm motion was not necessarily westward, but it was more so propagation to the west, where new updrafts would form on the western flanks of these ongoing storms, and that would give the illusion of westward motion. You'll notice that the strongest updrafts in this batch didn't really move a whole lot. We'll take this storm to the west of Padrone, for example. And you'll notice as I go through the animation here that storm really doesn't move a whole lot at all. It stays put. While we have new updrafts developing to the west of the ongoing storms, which behind this outflow boundary here, or this whatever this boundary was here, that gives the illusion of westward motion with these storms. Now keep your eye on this new updraft south of the ongoing storm between Akron and Otis. This would become our tornado producer. You can see it quickly develops into a supercell with a well-developed hook echo. It just kind of sits there south of Akron. Very classic presentation on radar. Precipitation vented off this way, hook echo there. Classic presentation of a supercell on radar. And the first real clue as to why this was able to produce tornadoes so prolifically was how discrete it was. Unlike the storms to the north, which constantly had to deal with new updraft generation on their western and southern flanks, leading to a more messy mode and the eventual dissipation of those storms. Take, for example, the Padroni supercell, the storm west of Padroni. Very well-defined supercell here at the start of the loop. Hook echo there. Very strong supercell. It tries to sustain itself for quite a while, but eventually has to deal with a bunch of new updrafts developing on its western and southern flanks, which leads to a more clustered storm mode, as you see here, and the dissipation of that initial updraft, and just an overall reduction of the tornado threat up there. Now, the southern storm near Akron that was ongoing at the time of that new updraft to the south, this was a well-developed supercell as well. These updrafts fired up to the south and southwest of the ongoing supercell. That storm dissipated, and then the new storm took over. And you'll notice that we don't see any additional development, especially to the south and southwest of this storm, leading to clear, unimpeded inflow and a lack of competition with other storms around it for those necessary atmospheric ingredients to produce tornadoes. And we've talked about this ad nauseum before on the channel, that discrete storms have a much better chance of producing tornadoes versus storms that are organized in more of a clustered or linear mode. And that's because a discrete storm does not have any storms around it to compete with for those necessary atmospheric ingredients for producing tornadoes, and its inflow can remain unsullied. Whereas if you have a storm in a line or cluster, it has a bunch of different storms that it's competing with for those atmospheric ingredients, and it thus has a much less chance of producing significant tornadoes than a discrete storm. And that's exactly what we got here. That Akron storm was all by itself for quite a while and was able to remain in an unsullied environment, especially to its south. Its inflow remained unimpeded, was able to take full advantage of the environment. Eventually, we did see a lot more updraft generation on its southern and western flanks, and we eventually got more of a clustered mode, and the tornado threat overall did diminish. But for several scans here, you see that storm was all by itself south of Akron, helping it to remain in a tornadic production state for quite some time. Next, let's take a look at a series of RAP model soundings in close proximity to the Akron supercell to determine some of the environmental factors that went into this prolific tornado producer. These soundings come from the town of Akron itself, so we have a really close proximity look at the environment surrounding this storm. We'll also take a look at a series of RAP soundings from Cheyenne, Wyoming, to get a picture of how the environment evolved much less favorably to the north in southeast Wyoming. But we'll start out at 12Z at Akron, Colorado, and to begin the day, we had a pretty classic loaded gun type thermodynamic environment in place. A moist layer, albeit a very shallow one, beneath a stout capping inversion just above about 800 millibars or so. Given a lack of upper level forcing for ascent, we'd have to rely on continued low level moisture advection and strong surface heating to erode this cap, but once that happened, rapid thunderstorm development should ensue, and that was expected given low clouds were starting to burn off across this area pretty early, and we'd have full solar heating going into the afternoon hours. Much of the same at Cheyenne, although you could argue a very much stronger capping inversion here at Cheyenne, just below about 700 millibars or so. Cooler surface temperatures to start off the day as well. So we'd have to have a bit more surface heating here. Again, we were a little bit closer to that trough, so that might help just a tad. A little bit of a glancing blow from that shortwave might help to lift and cool this capping inversion, but still, we'd have to really rely on that surface heating, and that's why that stubborn cloud deck was quite problematic. And I'm going to show in just a second why that may have allowed storms to remain a little bit elevated even as they came off the higher terrain toward the I-25 corridor. Back at Akron, you'll see that by late morning, the moist layer had deepened substantially. Here we are at 17Z, 11 a.m. Mountain Daylight Time, and that moist layer had deepened substantially. That red profile, the temperature profile, and the green line here, the dew point profile, pretty close together, up almost to about 700 millibars versus where we started the day with extremely shallow moisture there extending just a little bit above the surface. We had deepened that substantially by late morning thanks to that continued strong low-level moisture advection, given that those winds in the lowest couple kilometers were strengthening out of the east, really continuing to pump that moisture into the region. And we also saw those surface temperatures begin to spike up into the 70s as a result of that strong surface heating. And by 20Z, you'll see that we had a pretty pristine and upper echelon thermodynamic environment for Colorado standards that may even be slightly underdone. We saw on our surface map earlier that by this time we had temperatures that had soared into the low 80s here, only 77 being registered here on this RAP model sounding at 20Z from Akron. So this thermodynamic environment may even be a little bit underdone on this particular representation. Usually in Colorado, we're working with maybe 500, 1,000, 1,500 joules per kilogram of mixed layer CAPE. In this case, we have over 4,000 joules per kilogram of mixed layer CAPE. That is off the charts for this region, and it meant that updrafts were going to be quite explosive. And another thing that we always talk about on this channel that is our cheat code, and that is 0 to 3 kilometer CAPE, or 3 CAPE. That CAPE in the lowest, that instability in the lowest 3 kilometers of the atmosphere. The more 3 CAPE you have, as we know, the more chance there is for that any spin near the surface to be stretched into the vertical very efficiently to potentially aid in tornadogenesis in supercells. And you see here, we have quite a bit of 3 CAPE. 3 CAPE in excess of 200 joules per kilogram. That is extremely high. You see there in that lowest 3 kilometers, very, very fat CAPE here between our parcel trace and the temperature, the red temperature profile there. Very fat CAPE, over 200 joules per kilogram of 0 to 3 kilometer CAPE here at 20 Z, 2 p.m. Mountain Daylight Time. That is extremely high. For reference, anything above about 50 joules per kilogram is considered adequate. And we've undergone a rapid increase in 0 to 3 kilometer CAPE from the morning, where we had that capping inversion really thwart that 3 CAPE value, started out at 0, and quickly by mid to late morning we were up into the hundreds, and then by mid-afternoon or so up above 200 joules per kilogram there, 224 there on this wrap sounding at 20Z, 21Z, 243. That is just incredible 0 to 3 kilometer CAPE. So again, any spin near the surface was going to be able to be stretched very, very efficiently into the vertical to aid in tornadogenesis and supercells. And we can visualize this a bit better using our 3 CAPE and surface vorticity plot from the SPC Mesoanalysis archive for June 21st. As we've discussed before, the red contours represent 0 to 3 kilometer CAPE, and the blue contours represent surface vorticity or spin. Where the two overlap, you have a favorable environment where that spin can be stretched efficiently into the vertical to aid in tornadogenesis. And it doesn't take a genius to see the favorable overlap occurring there in northeast Colorado. You see as we go into the afternoon, that bullseye of 0 to 3 kilometer CAPE up there on the Colorado-Nebraska border, bleeding there into northeast Colorado, co-located with this area of surface vorticity. We've already established that there were several sources of surface spin or vorticity to work with. We had that frontal zone out to the east, that what the SPC was terming the remnant outflow boundary there in northeast Colorado, and also how the low-level flow is interacting with the terrain. All of that combined to create a very juicy environment in the low levels as far as surface vorticity goes. So when you have this much low-level instability with this much spin at the surface, this is a classic Colorado look for a tornado event, and in this case we were maxing out those parameters. Lots of surface spin, lots of low-level instability, so any sustained supercell in this environment will be able to take that spin, very efficiently stretch it into the vertical, increasing the chances of tornadogenesis despite at least somewhat weak low-level shear initially. Now up in Wyoming it was a different story. As we went into the afternoon, we saw some of the same trends that we did in Colorado, that cappy roads and instability builds, although much less than farther to the south in Colorado. And you have to remember that these soundings were taken from Cheyenne, Wyoming, which was well to the south of that stubborn low cloud deck where we were sitting to the north. And I can tell you as somebody who was underneath that cloud deck that it was definitely not 72 degrees as depicted by this 21Z Cheyenne sounding. It was quite cold, much cooler than 72 degrees. To make life easier, we'll say it was about 65 degrees. So if we were to plot our new surface temperature here, it would be somewhere right in there, and our new temperature profile would look something like that. That's going to have drastic impacts on the thermodynamic profile. If we were to plot our surface temperature and then plot our parcel trace, and if you're not familiar with how to plot the parcel trace, go ahead and check out my definitive guide to skew-tees and hodograph series from the playlists tab on my channel. This goes into in-depth on how to make your own skew-tees, including how to draw your own parcel traces. So basically we're going to go up from that new surface temperature along the dry adiabat, and then up along the mixing ratio line from the dew point. So our new lifted condensation level would be somewhere right in there, and then we draw in our parcel trace here, roughly something like that. And you can see what that cooler surface temperature does to the profile. It really diminishes the overall instability in the atmosphere, and we're also left with a little bit of a capping inversion here in the lowest levels of the atmosphere. So as that supercell northwest of Laramie moved toward the I-25 corridor, it struggled to become fully surface-based. Now, with terrain impacts and such, we were still able to get a brief tornado out of it, but I think the major downfall of this northern mode was the fact that we just couldn't quite fully destabilize here, especially along that I-25 corridor, because that cloud deck would not move out of the way. Therefore, cooler surface temperatures led to much less instability than what was modeled and what was being progged on some of the mesoanalysis products here. For example, this 21Z sounding at Cheyenne shows about 2,000 joules per kilogram of mixed layer CAPE. If we were to cool that surface temperature several degrees, you can see that that cuts it down drastically. And we also have to have some of that capping inversion remaining, which allowed any supercells that fired that down on the higher terrain to the southwest to move into this environment and struggle to become fully surface-based. Down to the south, we had no issues with low-level stability. In fact, as we showed, it was quite the opposite, with massive low-level instability helping to stretch that vorticity into the vertical. So we've started to develop the recipe for this Akron tornadic supercell, a discrete storm in an environment of strong surface vorticity and low-level instability. But that's a fairly common occurrence in Colorado tornado events. What was the difference with this one? Well, I have a hunch it was the anomalously high moisture and in turn very low LCLs. If you recall from some of our past videos, the LCL, or lifted condensation level, is the level to which a parcel of air must be lifted in order to become saturated. And it can be used as a rough estimate for the cloud base. We can think of the tornadogenesis process as a linkage between the rotation at the ground and the rotation aloft in the thunderstorm cloud. The lower the LCLs, or the lower the cloud bases, the easier it is for that linkage to take place. Typically in Colorado, we struggle to get super rich moisture like we had on June 21st. You have temperature dew point spreads that are very high, 82 over 55, 85 over 51, for example, which leads to very high LCLs. Now, the impacts of terrain and such can often help overcome this, but still that linkage that needs to happen during tornadogenesis is a bit tougher to achieve with those higher cloud bases. In the Akron case, we had much lower LCLs than normal thanks to that incredibly high low-level moisture. Very low temperature dew point spreads, 77 over 67 here at 20 Z at Akron. Of course, we talked about how that might be a little bit, that surface temperature is a little bit low. Temperatures were in the low 80s, but still 82 over 67, for example, is still an extremely low temperature dew point spread for Colorado standards. And thus we had very low LCLs, especially for this region, hovering right around that 1,000-meter range or so. Mixed layer LCLs here, about 980, again, a little bit higher because of that higher surface temperature as was observed, but still hovering around that 1,000-meter range or so. Here's some additional awesome footage showing just how low those cloud bases were. When you have such low cloud bases and such a rich reservoir of low-level vorticity as we had on June 21st, you're going to have a lot of opportunities for that tornadogenesis process to take place. And that's because it doesn't take much for any little eddy or area of spin at the surface to consummate that connection between the storm and the ground. You can see that's just incredibly low cloud bases for Colorado standards. So that spin doesn't need to be stretched all that much to interact with the supercell, but when you have such strong low-level instability and surface vorticity with these almost ground-scraping cloud bases, you're going to have a much easier time getting tornadic vortices. Now, a lot of these were brief and probably born along the rear flank downdraft gust front or little eddies carouseling around the mesocyclone. I'd kill to have some close proximity mobile radar data from this storm. Then we could really dive into the storm scale details, but still that tornadogenesis process was made much easier because that distance from the ground to the cloud base was fairly minimal. Now, there's one final question to ask, and it's about the wind profiles. As expected, we started off the day with very weak deep layer shear. Hodographs were quite small across northeast Colorado, effective bulk shear under about 20 knots, so very weak deep layer shear. And it would remain that way across northeast Colorado until about mid-afternoon. By about 20 Z, we start to see a notable increase in low-level and deep layer shear going into mid-afternoon, leading up to the time of the Akron tornadic supercell. You see by 20 Z, 2 p.m. Mountain Daylight Time, bulk shear up to about 27 knots, which is right on the margins for sustained supercells, and we continue that into the afternoon hours. 21 Z, we're up to about 33 knots of deep layer shear. And look at those hodographs, especially in the low levels by 22, 23 Z. Low-level shear balloons. 22 Z, we have effective storm relative helicity up above 200 meters squared per second squared. Very large looping hodographs at this point, and even more so by 23 Z, with effective storm relative helicity almost 350 meters squared per second squared, and very large looping low-level hodographs. That would be a result of those low-level winds increasing to about 25 to 30 knots or so, just about a kilometer or so off the surface. And those hodographs began to lengthen as well. You see a little bit longer, less compressed hodographs here by late afternoon, as that mid to upper level flow increased to about 30 to 40 knots or so in the mid to upper levels of the atmosphere. Certainly this hodograph is quite favorable for tornadic supercells. Large curvature there in the low levels, large storm relative helicity for any right-moving supercells to take advantage of. And of course, we had strengthened the deep layer shear up above 40 knots or so by this point. So deep layer shear, very favorable for supercells. Low-level shear, very favorable for tornadic activity with those supercells. So that begs the question, what caused this sudden change in the wind profiles? One hypothesis is that there was some sort of perturbation, in particular a small-scale mid-level jet that may have impacted the Akron supercell before and during its tornado production. And it may have been too small to be detected on any mesoanalysis data. And this is quite similar to what happened with the Moore, Oklahoma EF5 tornado on May 20th, 2013. Spoiler alert, I do plan on doing a full case study on the 2013 Moore EF5 in the very near future, so stay tuned for that, and we'll discuss this more in that video. But this was explained in a very detailed video by Chris Broyles from the SPC, who showed that the eventual Moore tornadic supercell was impacted by a small-scale mid-level jet streak, only a few miles wide by a few miles long, that provided a stark increase in low to mid-level flow and in turn low level and deep layer shear in the time leading up to the Moore supercell's tornado genesis. Something similar may have impacted the Akron supercell. We're too early for it to be a typical nocturnal low-level jet ramp-up that we see pretty much on a daily basis in the spring out on the plains. So it would make sense that a very small perturbation, like a little confined mid-level jet, impacted this area during the late afternoon, helping to increase low-level and deep layer shear, and in turn helping to increase the chances of sustained tornadic supercells. Of course, the surface vorticity and strong low-level instability likely were the driving factors for the most part as far as tornado genesis goes, along with those low cloud bases. But this increase in low-level and deep layer shear is very interesting and definitely could have been impacted by a very small-scale mid-level jet. So that's going to wrap things up for this video. Hopefully you learned a thing or two. As I said before, I really wish we had some close proximity mobile radar data from this storm, as we'd really be able to dive into the storm scale details surrounding the evolution of this supercell. But we have to rely on the environment in turn to really determine why this supercell was such a prolific tornado producer. As we talked about before, the discrete nature of the storm helped things out a lot, but also that strong low-level instability and surface vorticity. That surface vorticity was very easily able to be stretched into the vertical thanks to that very strong 3-cape. And that's kind of a Colorado classic, but that low-level moisture, that anomalously rich low-level moisture, really helped things out. Those cloud bases were pretty much ground scraping, so we had a lot of opportunities for any little area of spin or any little eddy to be stretched into the vertical to become a tornadic vortex. And also, as we talked about just now, that increase in low-level and deep layer shear toward late afternoon was very, very interesting. Just a hypothesis in that it could have been a little bit of a mid-level jet, similar to the Moore 2013 tornadic supercell. But more research is needed in that regard, and definitely was a case of very low cloud bases with strong low-level instability, strong surface vorticity that got the job done in producing up to 27 tornadoes from one storm, which is just absolutely prolific. So that's going to do it. Thanks for watching, and we'll see you in the next video.